welcome to this manufacturing process technology part 2 module 17. We were talking in the last module about the ion transport theory, and we assumed that in an ion environment there are many positive and negative ion centers, and each positive ion center has a cloud of negative ion centers around it and vice versa. So there are various motions which happen in such a system which is otherwise electrically neutral. The first motion that can be imagined is basically the random walk or the thermal motions of the ions, which would be completely randomized. Excuse me. The other motion that is suggested is basically a sort of clouding of the opposite charges around the central ion of interest of the opposite type. So, if supposing the central ion is positive, we should have an ion cloud formulation around it of the negative ions and vice versa. And in the third module, what we saw is that if we put an electrical potential in such a system, there is a tendency of the electrons or the negative ions to move towards the positive electrode and vice versa, and in the process of it, all these ion clouds or ion atmosphere kind of gets reformulated and disrupted from place to place. So, it is like a hopping mechanism that these charges would follow, so that the bulk movement of positive charge happens towards the negative electrode and vice versa. So, we also started understanding how we can actually develop a potential function around the charge based on an otherwise electrically neutral medium, where we can assume a certain density function at a distance of infinity from a central charge of interest. And in this context, we laid out this famous Debye-Huckel theory and tried to started to sort of derive it, that let us say there is a central ion of interest which is positively charged, and around a point around this charge is a point A where the potential function is given by psi A. We also assume that there are about close to n plus 0 and n minus 0 positive and negative ions per unit volume at a distance radius r equal to infinity from this particular ion of interest, the positive ion of interest. And having said that, we tried to sort of find out that if we wanted to bring a positive charge which is having Z plus valency, or a negative charge which is having Z minus valency near this ion at the point A from the point infinity, the total amount of work that is done for the positive charges would be then given by plus Z plus epsilon times of psi A, where psi A is the potential function at A and E is the electronic charge, which is 1.6 into 10 to the power of minus 19 coulomb. And similarly, for the negative charges, an identical kind of work would be done by the positive charge or by the system given by minus Z minus epsilon psi A. Okay. So, this point A is actually a point in the vicinity of the positive ion, where the potential function is assumed as psi A. So, if we apply the Boltzmann distribution here, so from Boltzmann distribution, n plus could be obtained as n plus 0 e to the power of minus Z plus epsilon psi by small k times of t, and n minus, which is actually the number density near the at the point A. So, we can call of this as number density at point A, okay, where the potential function is psi A, is given by n plus 0 e to the power of minus Z plus epsilon psi A by k t. K is the Boltzmann constant. So, I am not going to go into the derivation of how we arrive at this, but we will just merely explore whether the boundary conditions are obeyed as far as this equation is concerned. Okay. So, we have a K as the Boltzmann constant. And we can assume here that at a distance r equal to infinity, the xi a would typically go to 0, which would make the n plus at infinite distance away from the positive ion as n plus 0 and n minus 0, putting the value of xi a equal to 0 in these two equations 1 and 2. Okay. And similarly, at a certain temperature, which is a very low temperature, let us say at absolute 0 temperature T equal to 0, this factor here would be very small. Okay. And so, the n plus or the charge density at the point A because of absolute 0 temperature would be actually equal to 0, which is also a true assumption in this particular case. So, if I consider the subscript I in a manner so that Ni is the total number of ions, be it negative or be it positive, of either kind per unit volume, and we wanted to find out the electrical charge density at the point A in the near vicinity of the central charge, this would come out to be equal to rho is n plus z plus epsilon, where z plus is the valency on the positive ion, minus of n minus z minus epsilon, where again n minus is the number density of the negative charge, and z minus is the valency on the negative ion. So, we can actually write this down as n plus 0 z plus epsilon e to the power of minus z plus epsilon xi by kt, k being the Boltzmann constant, minus of n minus 0 z minus epsilon e to the power of minus z minus. So, therefore, it is plus z minus epsilon psi by kt. This is I a, the potential at the point A in the near vicinity of the charge, which is the central charge. So, if I were to apply Taylor series here, so that the higher order expressions of the series representation of the exponential function can be neglected, we can sort of approximate the exponential function. We know that Ex is represented as a series function by 1 plus x by 1 factorial, x square by 2 factorial, so on and so forth. So, if we neglect the higher order terms, we can easily have e to the power x being represented as 1 plus x, and we put that back into this particular equation for the net charge density, let us say equation 3. So, putting the Taylor approximation in 3 will result in n plus 0. So, rho basically the overall electrical charge density n plus 0 z plus epsilon times of 1 minus z plus epsilon psi over small k t minus of n minus 0 z minus epsilon 1 minus z minus epsilon xi, this I a, I am sorry, divided by small k t. So, if we open this up, we are left with an expression n plus 0 z plus epsilon minus n minus 0 z minus epsilon as one term, minus of n plus z plus epsilon square psi of a by k t minus of n plus I am sorry n minus 0 times of z minus epsilon square times of psi a by kT. So, the first term here, based on the principle of electron neutrality, which holds true at infinite distance, you can assume that there is no influence of the central charge at a distance r equal to infinity from the charge itself. So, there is exactly equal number of positive and negative charges, Therefore, this whole expression here, n plus 0 and n minus 0 are same to each other. So, this is the average number density of the charges at r equal to infinity. So, this becomes equal to 0, okay, and we are left with only two terms here, which is n plus 0 z plus epsilon whole square xi a by kT plus n minus 0 z minus epsilon square psi a by kT. So, we can represent this as minus of Ni with a sigma, where sigma is a summation of all different charges varying between 1 to, let us say, n charges, where n includes both positive as well as negative charges, Zi square epsilon square xi a by kT, and this becomes equal to the charge density rho at the point in the near vicinity of the positive central charge of interest as represented. So, if we wanted to look at the expression that comes out, let us just record it here, rho becomes equal to minus sigma Ni Zi square of epsilon xi a by kT. Let us call it equation 4, and this will be referring to, because we will be needing this to really solve the potential the equation involving the potential function, and try to find out what is the potential at A based on some of these presumptions. So, if we look at the electrostatic potential xi A, it is related to the rho or charge density function at A by Poisson's equation, and this can be represented here by del rho xi A by del x2 plus del rho xi A by del y2 plus del rho xi A by del z2 equal to minus 4 pi rho by d. So, let this be equation 5. So, we first apply a sort of coordinate transformation here, try to get it converted into a spherical coordinate. You have to remember that the central ion of interest is actually a spherical ion, at least that is what we are assuming it to be. So, we use a coordinate transformation to convert into spherical coordinates. So, here obviously we consider this to be a symmetric distribution of charges, which is really creating a potential function which is also a symmetric distribution, and it is only a function of r. So, it is a function of radius r. So, assuming that, so we have this equation right here converted into 1 by r square del by del r times of square of r del xi a by del r times of r square becomes equal to minus 4 pi rho by d. Or in other words, I can substitute the value of rho from equation 4 right here. I can write this as minus 4 pi d root of or sigma Ni Zi square times of square of epsilon xi a by kT. or this becomes plus minus of minus. So, this actually represents now the final form of the equation. So, if we want to solve it, let us assume a term capital K, which is actually given as 4 pi by d square of epsilon by small k t Boltzmann constant times sigma ni zi squared. Just for the sake of convenience, we are assuming this is an any even constant. Okay. So, we can represent this whole expression here 1 by r square del by del r square del xi a by del r as k square times of xi a. So, this equation here right here, we can call this equation 7, has a general solution provided by xi a as a function of r is a to the power of minus capital K r by r plus a dash e to the power of plus k r by r. So, this is the general solution, and we can apply the boundary conditions here to solve for the unknowns, which are the coefficients a and a prime. So, we already know that there is one boundary corresponding to r tending to infinity, where the xi a becomes equal to 0. There is no influence of the central line of interest at a distance infinity from the ion of interest itself. So, in that event, this possibility only can happen if a dash is 0, because at r equal to infinite distance, this will go to infinity and this will go to 0, and so therefore, definitely a dash has to be 0. In other words, xi a can be represented as a to the power of minus capital K r by r. Okay. So, if I substituted this value back into equation 4, which was about the density function. So, the density here was represented as minus sigma ni zi square of epsilon times I a by small k t, and I represent the value of xi a into the expression. So, this becomes equal to minus ni zi square epsilon square by Boltzmann constant k times of t times of a to the power of minus capital K r by r. And already we know that the value of k square, capital K square, has been represented as 4 pi by d epsilon square by small k t times of sigma ni zi square from the last equation. So, this whole term right here ni zi square times of epsilon square k t can be written down as equal to k square, capital K square times of d by 4 pi. Okay. So, I would like to now substitute this back into this expression for rho. So, the rho becomes equal to minus of d capital K square by 4 pi times of a to the power of minus k r by r. And this is how you define the value of the charge density rho. So, our goal now in this whole process would be to establish this unknown, which is a, and this can be again brought by creating a sort of charge balance equation, because we know that otherwise the medium is electrically neutral. So, if I had a central ion of interest which is positively charged and there is an ion cloud around it. So, obviously for electroneutrality's sake, the values of the charges of the central ion should match with that of the ion environment in which this ion is present. Okay. So, for electroneutrality's sake, for neutrality the total negative charge, assuming the central ion to be positive, of the atmosphere about a given ion as exactly minus Zi epsilon. Okay. The total charge in the atmosphere around the central ion of interest can be determined by a spherical shell of thickness small dr and distance small r from the central ion. Okay. So, we can have this positive charge sitting right about here, and we can also have basically a radius function a, and we can also have a spherical shell around this, which is at a distance r from the central ion, and have a thickness dr, okay, represented by the volume, elemental volume times charge density function. Okay. So, if you assume only one central ion and an atmosphere around it, we have the elemental volume of this small spherical shell as 4 pi r square dr. So, with this dV times of rho as the total charge in the spherical shell, if I integrate the shell from the value a all the way to r equal to infinity, which is assumed to be for completeness a single ion balance, complete balance. So, a to infinity, this should be essentially equal to the charge density minus Zi epsilon. Okay. And this is more so because obviously the ion here of the central of the central ion here would be having exactly the same magnitude of charge at the atmosphere around it. There is no more positive ion in the whole system. That is what we are assuming. We are assuming only one central positive ion, okay, in this whole derivation. So, therefore, we substitute the value of rho from the previous step in this expression here. We get rho from the previous step was minus a square of k by 4 pi dielectric constant d to the power of minus kr by r. So, if I substitute that here, we get integral a to infinity 4 pi r square times of minus a capital K square by 4 pi d e to the power of minus capital K r by r times of dr should be equal to minus Zi epsilon. So, the 4 pi goes away, the r goes away, and we are left with an expression a square of k times of d integral a to infinity r e to the power of minus capital K r equals Zi epsilon. So, if I am able to solve this value with the known terms, because I already know what is the valency which is into question, I already know what is the k value, I already know what is this function here between a and infinity, the dielectric constant of the medium. So, I would be able to solve for the unknown, which is k in this particular which is a in this particular equation. So, let us now integrate this expression by parts. kind of recall that the integration by parts expression says any integral fx g dash x dx from a and b, a to b, can be represented as fx gx a to b under the limits a to b minus integral of a to b f dash x gx dx, right. So, our first function is in our case the value r, and our second function g dash x in this particular case is e to the power of minus kr, meaning thereby that the first function fr is r and the second function gr, okay, because g dash r is already e to the power of minus kr, becomes equal to minus e to the power of minus kr by k, okay. So, that is how gr can be represented. So, if I put this or substitute this back into this by parts formulation, we have integral a to infinity, b is infinity in our case, r e to the power of minus capital Kr, which we need to calculate in the last step, becomes equal to minus r e to the power of minus Kr by k between limits a and b minus of, and so now we have one expression which is f dash r, which is 1. So, we have only minus of e to the power of minus capital Kr by k times of dr integral a to infinity. This b is infinity in our case. So, that is how we write this expression, and when we solve for this particular integral, this comes out to be e to the power of minus kr by square of k between limits a and infinity, okay. So, this thing is solved here, and the first expression which comes out corresponding to infinity, r equal to infinity, is 0 minus of minus, that is positive a e to the power of minus k a by k, and the second calculation of the limits here becomes equal to plus e to the power of minus k a by square of k. So, that is how you solve this by parts, and if I substitute this back into the expression that was obtained earlier, which was a capital K square d times of this integral right here, whose solution is given as a e to the power of minus k a by k plus e to the power of minus k a by k square equal to z I epsilon, I would have a solution for the value a, and this can be represented here as further z I epsilon e to the power of capital K a divided by d to 1 plus capital K a, okay. In other words, if I put this back into the expression for xi a, my xi a is recorded as a e to the power of minus capital K r by r, which is equal to z I epsilon e to the power of K a times of e to the power of minus K r divided by d 1 plus capital K a times of r. So, obviously, that is how you can have your potential function in a point A which is in the near vicinity of the main charge equation. Further, if I wanted to sort of see what is the contribution from the ion and what is that from the atmosphere, I can resolve this in a manner that it can be calculated at the point r equal to a. If I substitute that here, these are going to go away, and we are left with the potential function at the surface of the charge as z I epsilon divided by d 1 plus k a times of a. And if I wanted to further resolve this into partial fraction, I would be left with two terms here. I can write this down as Zi epsilon by d times of 1 by a minus capital K by 1 plus capital K a. Okay. So, obviously, the first term would be due to the ion itself. So, that is the contribution from the ion itself, but what we are interestingly seeing here, that there is also a contribution from the atmosphere back to the ion, which can be represented as Zi epsilon k by d 1 plus K a. In other words, I can also represent only this part as Zi epsilon by d times of 1 plus K a by k. Okay. So, this right here is the effective radius, you can say, just because this was the radius of the ion, of the central ion, this could be the effective radius of the ion atmosphere. So, as you are able to see here, that when we are talking about the central ion of interest and a point around A, which is at the surface here, there is a contribution from the ion itself. There is also a contribution from the atmosphere itself. The ion's radius obviously is A, given by this part of the potential function at the surface corresponding to r equal to A, and the other part here comes from the environment, is given by the if it's an effective radius, which is 1 plus K a by k. So, with this I would like to end this particular module, but in the next module I am going to look at how you can apply, instead of a single charge, if I had an ensemble of charge on the surface, can we really find out a potential function close to the surface because of the series of such charges trapped within the solid electrode. So, with this I would like to end this particular module. Thank you so much.